ruler. So, as the title of the chapter suggests, quantities in chemical reactions. So, this chapter is going to be our next chapter, which has a lot of concepts based on chemical calculations. Continuation of chapter 4. What you learned in chapter 4, the mass mole conversions, will be used again here. Let us look at the chapter topics. The topics we would cover is, first we will look at what is the meaning of a balanced equation. So we learned how to balance equations in last chapter, and we are going to look at the meaning of those coefficients in the balanced equation, and then we will do mole-mole conversions, mass-mass conversions. So as you can see, those two will closely relate to the dimension. I mean, we are using dimension analysis in every single problem. So far you have seen that. So we will use the concepts from chapter 4 here, and then something called limiting reactant, percent yield. We will also look at energy changes, mainly heat energy that is released or absorbed during a chemical reaction. How do we quantify that? Okay? And heat changes in chemical reactions. So these are the topics we would look at. So, as an introductory question, this is what first we are trying to understand. How can we predict the amount of products or reactants you will require in a chemical reaction? A chemical reaction is not carried out by, picking up things from here and there and you just mix it. It has to follow a recipe. Okay, how much of what should be mixed with how much. So how can we make those calculations? How can we predict how much is required to react with one reactant so that you can produce a specific amount of product? That kind of calculations. Now we will just first look at, just as an example, an internal combustion engine, ICEs, which we use in our cars. And how can we predict the amount of heat generated or absorbed during a reaction? That also we will look at in the end of the chapter. So in an ICE, octane, fuel we put in, burns with oxygen from air to produce hot gases that push against the piston to do work. This is a schematic of an single cylinder internal combustion engine. So you have fuel-air mixture. Fuel has to mix in a particular ratio with air, and it is a high temperature combustion process. As you can see, look at the temperature inside your car engine, 2500 degrees Celsius. Okay, that's a very high temperature, and that reaction, the octane burning with the oxygen, produces a lot of heat energy and hot gases, and that will push against the piston, and that piston, I'm not going to the details of how the car runs, okay? So that's it. We are just, focusing on how can we make sure how much octane reacts with how much oxygen. That's what we are after, the quantities that would react. Now, the amount of oxygen that react depends upon the amount of octane that burns. Again, the amount of energy produced also depends upon the amount of octane that burns. So we are after that ratio, or that recipe of octane and oxygen. Now, just as a matter of fact, even after all this research on high efficiency, we are talking about producing high efficiency cars and making good engines and all that, still our overall efficiency is 20 to 25%, meaning thereby 75 to 80% of the energy in octane is wasted as heat. Okay, so that is why there is so much heat produced when the car runs, and most of it is, some of it in the winter months we will use to heat the inside of the car. That heat from the engine, we will direct that towards the inside. That's how when we run the fan on the heat setting, we get hot air. But otherwise, that energy is all wasted to the atmosphere. Okay, so we are still working on how to improve the efficiency, probably after all this research, might be a better idea now to start looking into alternative fuel cars. Anyway, in a balanced equation, we know that we use coefficients to specify the amount or the proportion of the reactants that react and the proportion of the products that will form. Let us look at the combustion of propane. Propane is also a fuel. Propane is the gas you use in your grills. The propane tanks you buy, that has propane gas. Propane also burns with oxygen, producing a flame and a lot of energy, and that's what you use to cook food in your grill. So propane, which has the formula C3H8, reacts with oxygen, and propane burning is, if your gas grill is clean, then you have a good combustion which produces only flame and carbon dioxide and water. Remember the products of a combustion reaction, carbon dioxide and water. So here is the reaction given. The reaction is balanced for you already. So one molecule, this is an implied one here, right? When we don't see a number. And 5 of oxygen molecules, 3 of carbon dioxide and 4 of water. That is how we balance the equation, and it is given in the picture also. If you count, that's what you will count, each of them. So in this balanced equation, these coefficients we use, the coefficients means again 1, 5, 3 and 4, those are the coefficients, not the subscripts in the formula. The coefficients in the balanced equation tell us about the relative number of reactants that combine and products that would form. And as I said, whenever you don't see a number, you would assume it is 1. So this means for every molecule of propane that reacts, it will require 5 molecules of oxygen, and then the reaction will produce 3 molecules of carbon dioxide and 4 molecules of water. And that is what, as I said, that picture shows again. 1 molecule of propane, 1, 2, 3, 4, 5 molecules of oxygen, and you have 1, 2, 3 molecules of carbon dioxide, 1, 2, 3, 4 molecules of water. So the picture also shows what we see in the balanced equation. So the coefficients in the balanced equation, we looked at this point in the lab briefly. I have told you guys in a particular reaction, what do the coefficients actually mean? It's not just the molecules, it gives you the mole ratio, those numbers in front of your balanced equation. That tells you how many moles of each of those reactants are combined and how many moles of each of those products are formed. Okay? So it would give us the relative number of moles of reactants and product. So this equation can be explained in this way. For every mole of propane that reacts, how many moles of oxygen is required? 5 moles of oxygen is required and 3 moles of carbon dioxide is produced along with 4 moles of water. Okay? So those numbers, it just becomes the mole ratios between the reactants and products. This can be, if you are still not convinced, this table should make you convinced. Okay? So the balanced equation, and of course what we see here is 1 molecule of propane, 5 molecules of oxygen, 3 molecules of carbon dioxide and 4 molecules of water. Now let's say instead of 1 molecule, what if I start with 2 molecules of propane? I need to double everything, right? It's just like when you are making cookies. If you want to make a dozen of cookies, let's say the recipe starts with 3 cups of flour and whatever, eggs, butter, all other stuff. But what if you want to make 2 dozens of cookies? Then you would start with 6 cups of flour, right? So accordingly you will double all the other ingredients too. So that is the same relationship here. Instead of 1, if I'm starting with 2 molecules of this, everything else also gets doubled. Now let's say instead of doubling, I'm making it 100 times. Instead of 1 molecule, I start with 100 molecules of C3H8. So you are looking at the relationship here. Instead of 1, it is 100. That means everything else also will get multiplied by 100. So you got the point. Now let's say instead of 100, I'm starting with 6.022 into 10 to the power 23 molecules. Hey, that's the number. And I can start with that. What does this number mean? How much I have? This number means I have 1 mole of propane, because this number specifies how many molecules you have in 1 mole, right? So if I'm starting with this number of propane, that means I have 1 mole of propane. So you got the relationship now. Whatever, 1 molecule is what I started with. If I make it 6.02 into 10 to the power 23, everything else also should get multiplied by that number. So 5 times 6.02 into 10 to the power 23, meaning thereby you have 5 moles. 5 times that number is 5 moles. Similarly, 3 times that number is 3 moles, and 4 times the number is 4 moles. So basically, instead of molecules, you are just thinking of them as moles. That's all. Okay? So when we look at the balanced equation, the coefficients tells you what is the number of moles of each reactant you will require and what is the number of moles of each product that will form. Now, the process of determining the amount of a reactant or a product from the amount of a reactant or a product is called stoichiometry. And that's what we are going to do in this rest of this chapter. Okay? So in a chemical reaction, if you have the balanced equation, and if you know the amount of any of the reactant, any one of the reactant or product, you can calculate the amounts of all other reactants and all other products. That's the beauty of stoichiometry. All you need to know is just the amount of one item from the balanced equation. So that's what we are going to do now. Let us again use the example of propane burning. Now, to do stoichiometric calculations, we will use a mole ratio. Okay? So, mole ratio will relate the number of moles of one reactant or product to another. And where do we get the mole ratios from? From the balanced equation. That's what we just said. The balanced equation, those coefficients tells us the mole ratio. So we get the mole ratios from the balanced equation. Say for example, what is the mole ratio of oxygen to propane in this given equation? You are looking at the given equation and it says 5 moles of oxygen will react with 1 mole of propane. So pay attention to the words. It says oxygen to propane. So we will write the ratio as 5 to 1. If I ask you what is the ratio of propane to oxygen, then you will write 1 to 5. However, that is not the format we will need to do the stoichiometric calculation. Remember, mathematically, a ratio is also a fraction. Every ratio can be written as the fraction. The first number you see in the ratio will be the numerator. The second number you see is the denominator. Okay? That is how you will write as a fraction. And that is the format we will require to do the dimension analysis in our problems. Just this format of the ratio will not help us. Okay? So, oxygen to propane mole ratio would be 5 moles of oxygen per 1 mole of propane. And we don't have to calculate that from anywhere. We can see that clearly from the balanced equation. You tell me now, what is the ratio of carbon dioxide to oxygen? 3 to 5, but which format? Let me in the fractional format. I am trying to make you see in that format. 3 moles of carbon dioxide per 5 moles of oxygen. How about the ratio of carbon dioxide to water? 3 moles of carbon dioxide per 4 moles of water. You got it. So that is the format we will require for the stoichiometry calculation. Now, the mole ratio would allow us to calculate this. So we were just talking about the oxygen propane mole ratio, and that mole ratio would allow us to calculate the amount of oxygen that will react with any amount of propane. If you know that mole ratio from the balanced equation, as I said, all you need is what is the amount of one of the item. You can just calculate everything else. You don't need to know specifically how much you need to put in. You can calculate that. So we will use the mole ratio as a conversion factor in the dimensional analysis. That is why we need that fractional form of the mole ratio. So let's say, for example, if I tell you I have 0.40 moles of propane, how much oxygen I should mix with 0.40 moles of propane? How do we calculate that? So we will set it up just like the dimensional analysis. How do you do the unit conversion? What am I given? I am given 0.40 moles of propane. So I'm starting with that. And I multiply by the mole ratio, because mole ratio is my conversion factor. What am I looking for? I am looking for moles of oxygen required. So that should go in the numerator. 5 moles of oxygen per 1 mole of propane in the denominator. So that again units also would cancel perfectly, and you will end up with the number of moles of oxygen required. So 0.4 multiplied by 5 divided by 1 will give you 2. So if you are starting with 0.4 moles of propane, you should need 2 moles of oxygen to react with that. So just like this, we can calculate how much carbon dioxide will be produced and how much water will be produced if you start with 0.4 moles of propane. Right? All we need is the corresponding mole ratio written in the fractional form. So this is the heart of stoichiometry, the mole ratio conversion. Okay? So let us take another equation and let us practice some. Here is another fuel, benzene, C6H6. It's an organic solvent. Burns in air according to the following equation. So here 2 benzene reacts with 15 moles of oxygen, producing 12 moles of carbon dioxide and 6 moles of water. That's the balanced equation. Remember guys, to do stoichiometry problem, you need a balanced equation. You will always start with a balanced equation. Okay? And I will give you the balanced equation when you do any of the stoichiometry problems, because if you go wrong in balancing the equation, your entire question goes wrong. I mean, entire problem goes wrong. So just to avoid that part, I will give you the balanced equation when you do a stoichiometry problem. But that is your starting point, because the balanced equation gives you the mole ratios. Without mole ratios, you cannot do stoichiometry. Okay? That's why balanced equation is your starting point. Now, the first question is, what is the mole ratio of oxygen to benzene? What is the mole ratio? 15 moles of oxygen per 2 moles of benzene. So that would be the first one. Now, let us answer the second one. How many moles of oxygen are required to react with each mole of benzene? So if you have only 1 mole of benzene, how much oxygen you will need? How many moles of oxygen you will need? 7.5. Well, we can just do that overhead, or if you want to write it down as the mole ratio problem, because everything won't be that easy, right? It won't be like easy numbers like that. Let us, what's the problem? Pointer. And ink. So we have 1 mole of C6H6 and we will multiply that by the mole ratio. We are looking for moles of oxygen, so that part goes in the numerator. 15 moles of oxygen per 2 moles of C6H6. This would be the dimension analysis setup. So moles of C6H6, moles of C6H6 get cancelled, and the math you are doing is basically 1 times 15, 15 divided by 2, which is 7.5. So you will require 7.5 moles of oxygen. This would be the setup. But as I said, this one you can just do it overhead because the numbers were whole numbers. Now let us do this one. This one may not be, you may not be able to do it overhead. You may have to set it up. How many moles of oxygen are required to react with 0.38 moles of benzene? So how do I set that up? Where do I start? 0.38 moles of benzene, that's what I'm given. So 0.38 mole of benzene multiplied by my conversion factor, which is the mole ratio. And how will I use it? Which on the top, which in the bottom? The 15 moles of oxygen on the top and 2 moles of benzene in the, it's 6 in the denominator. And not that, that ratio is directly taken from the balanced equation. You are not calculating that in any way. So do the math please. What is the math we have to do? 0.38 multiplied by 15 divided by 2. Or 0.38 multiplied by 7.5, whichever way you do. What do you get? How many moles of oxygen you will need? 2.95? 2.85. That's the amount of oxygen you will require for 0.38 mole of benzene. Let's see, I think I have, well, right there, everything has been done for you. And we are writing 2.9 moles in the answer slide because look at the 0.38. How many sig figs? Only 2. So we need to express our answer with 2 sig figs. So 2.9 moles of O2. The same, oh no, it's not the same equation. It's the propane equation. Propane burning with oxygen. Here we are trying to do first, what is the mole ratio of carbon dioxide to oxygen? I think I had asked you this question. You know this. How will I write that mole ratio? 3 moles of CO2 per 5 moles of oxygen. That is the mole ratio. Now the second question is, how many moles of carbon dioxide will be produced when 2.3 moles of O2 reacts? How do I set up this one? So what am I given in this problem? 2.3 moles of O2. So I'm starting with that. 2.3 moles of O2, and I need to multiply that by a mole ratio. You tell me what should be the mole ratio. Which mole ratio should I use there? 3 moles of CO2 per 5 moles of O2, because I'm looking for moles of carbon dioxide. So that should be in the numerator, and the balanced equation says carbon dioxide's mole number is 3. So 3 moles of carbon dioxide per, and I'm using oxygen, so 5 moles of oxygen. Again, your units also will cancel perfectly, and you will have the answer in moles of carbon dioxide. So 2.3 multiplied by 3 divided by 5, 1.4 moles of carbon dioxide will be produced. An additional question, how many moles of water will be produced if 2.3 moles of oxygen reacts? How will I set it up? Same amount of oxygen, I am just changing carbon dioxide to water. How will we set it up? So again, I am starting with how much water will be produced? 2.3 moles of O2 multiplied by Yes. This time I'm looking for water. So 4 moles of H2O per 5 moles of oxygen. That will tell me how much water will be formed. 1.8. So you can, again, if you want to do one more step, that is, if you are curious, you want to know how much propane will react. Let's do that. If you have 2.3 moles of oxygen, how much propane will react with that? How will I set it up? 2.3 oxygen multiplied by, I'm trying to write it in short form. 1 mole of propane per 5 moles of oxygen. Yes. So 2.3 divided by 5. 0.46 moles of C3H8. So this is what the beauty of stoichiometry is. All you need is the balanced equation and the amount of one substance in it, either a reactant or a product. And using the mole ratio, you will be able to calculate the amount required for the complete reaction of all other items. Here is a different equation. Aluminum reacting with chlorine gas forming aluminum chloride. I think aluminum chloride, well, they've given us gas. Aluminum chloride is usually a powder, solid. Anyway, doesn't matter. The physical state is not going to affect our calculations here. So we are after stoichiometry. So let's forget about that. So the question is, how many moles of chlorine are required to produce 0.62 moles of aluminum chloride? So we have 0.62 moles of aluminum chloride. How much chlorine are you reacting? It's the same. We are starting with what we are given. What are we given? 0.62. It's just the wording is a little bit different. That's all. Same concept. We are given 0.62 moles of aluminum chloride. We are going to multiply that by the mole ratio. What mole ratio we should use here? We are looking for moles of chlorine. So 3 moles of chlorine on the top and 2 moles of AlCl3 in the bottom. So don't get confused when you read the question using different words. It means the same. Okay? Whatever you are given, carefully see what are you looking for. Use the mole ratio between those two items from the balanced equation. That's all the crux of the problem is. So cancel the units, and what do we have here? How many moles of chlorine you will require? 0.93. Yeah, it's right above mine, so I'll put it like that so that if anyone is still looking at it. So got the idea how to use the mole ratios? Okay. Clicker. And where is my clicker icon? Give me a second, guys. Where is that? There. Okay. All right. Here is the equation we have been working on, the propane burning equation. You have 2.7 moles of propane. How many moles of carbon dioxide will be formed? That's what it's asking. So set it up and do the calculation, please. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Do you all have clickers? You didn't bring? You forgot. Not in the car? Okay. All right, so 18 then. What? Using clicker? Oh, really? I don't think that will work. It will accept only the data from clickers, not from the calculators. We all need that break, I hear that. It's right about that time where, the brains are like, I need a break. How many I counted? Oh my, I'm too old. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. And you said you don't have, so 18. You remember, 18. Another 30 seconds. What do we need to do here? It's a single step conversion, single step calculation. You all you told me you don't have clickers. Everyone else have clickers, right? What? Well, it's not a big calculation. You all know how to calculate it manually. It's a single multiplication step. So please do it on the paper. How did we learn multiplication, division, all that stuff before calculators? Oh my, we're stuck on 16. Okay, I'm going to stop the clock at the 4th minute. So please do it before then. There. How would I set this up? I am given 2.7 moles of propane. So, oops. Where is my pen pointer? Oh, come on. So 2.7 moles of C3H8 multiplied by, I'm looking for moles of carbon dioxide. So 3 moles of CO2 on the top and 1 mole of C3H8 in the bottom. So what is the math you need to do? 2.7 multiplied by 3. You can even take a guess on that. You don't need a calculator to do that one. The only one option is 8.1. When you multiply by 2.7 by 3, obviously it has to be a larger number than 2.7, right? Okay. Let's see. I do have 16 correct answers. All right. So the next topic we are going to do is mass to mass conversions. Okay? We were doing the mole ratios, we were understanding the mole ratios, how the reactants and products are related in terms of the moles. But in reality, when you perform a reaction, we know this. We don't have an instrument that would measure number of moles. What do we measure commonly? We measure the mass in grams, right? So we need to know, if you know the amount of a reactant or a product in terms of its mass or the grams, how can we calculate the grams of some other reactant you will require or grams of one of the product that will form? Okay, so that's what we mean by mass to mass conversions. So we will pick up formation of sodium chloride equation. Balanced equation is given to you. 2 sodium reacting with 1 mole of chlorine gas forming 2 moles of sodium chloride. And the question we have to answer is, what mass of chlorine gas is required to react with 9.20 grams of sodium? So sodium, one of the reactant, mass is given to you, and it's asking what mass of the other reactant you should use. We cannot, as we say, we just said, we don't measure the reactants and products in number of moles, but we measure their mass. And the balanced equation does not tell us a mass relationship, okay? The coefficients in the balanced equation gives you only the mole relationship, not the mass relationships. So you cannot directly use the mole ratio on mass. So the heart of the problem remains the same as so far we have done, but we just have to add 2 side steps, one in the beginning, one in the end. Okay, what would be that? Converting grams to moles and then doing the problem using mole ratio, and then finally the question is asking what mass of chlorine gas, so converting moles to mass. So that conversion we learned in chapter 4, mass to moles, moles to mass. We will just use that in the beginning and in the end to completely answer the question. Concept remains the same. Okay, shall we start? Okay, so here is what we are given. This is the balanced equation. We are given 9.20 grams of sodium. Now, here is something I'm going to tell you in every class from now onwards. In stoichiometry, whenever you see an amount in grams, before even thinking what am I doing in this problem, convert that to moles. Using what? Molar mass. You will always have a periodic table. You will know the formula of the substance. So take the molar mass, convert the grams to moles. You will not do a stoichiometry problem relating mass to mass. You will always need to relate moles to moles. Okay? So that is your first step you will do. We will convert grams to moles using the molar mass. Again, as it says, see section 4.2 if anyone is still wondering about how do I convert mass to moles. As I keep saying, we are very, very cumulative. So please, you cannot leave anything behind. How do we convert mass to moles? Using the molar mass. Using the molar mass as a conversion factor. So this is what we are given, 9.20 grams of sodium. And here is the molar mass of sodium. You will see in the periodic table, 22.99 grams is 1 mole, and you are using that as the conversion factor. We are looking for moles, so mole part in the numerator, grams part in the denominator, and we will find out the number of moles of sodium. Now you can do the mole ratio part, because now you know how many moles of sodium you have. Now you can read the question in this way. If you have 0.400 moles of sodium, how many moles of chlorine is required? So you can calculate the number of moles of chlorine required. Now that is your second step. So relating the moles of chlorine to moles of sodium, As I said, this is the heart of the problem which you have been practicing so far. So moles of sodium, which is 0.400 moles, multiply that by the mole ratio from the balanced equation. What is the mole ratio says? 1 mole of chlorine per 2 moles of sodium. So that's what you are using here, 1 mole per 2 moles, which will give you number of moles of chlorine. Is the original question asking what moles of chlorine required? No, it's asking what mass of chlorine required. So what is the last step you need to do? Converting this moles of chlorine to mass of chlorine using what? Molar mass of chlorine. So that's the last step you are going to do. So the conversion of moles of chlorine to grams using the molar mass of Cl2. Pay attention here. The substance you have is Cl2, not just one Cl. So remember to use the molar mass of Cl2. That is how you have 70.90. So using the molar mass, you converted the moles of chlorine to mass. Now the question is complete. This is the final answer you are looking for. The question is asking what mass, and there it is. We have everything. So if you look at this question once again, this is where we started. We were given this quantity, mass of one of the reactants, 9.20 grams of sodium. We converted that to moles using molar mass of sodium. Then we did the mole conversion using mole ratio. The question was asking what mass of chlorine. So one more mole mass conversion, converted the moles of chlorine to mass of chlorine using. So this part, that conversions were from chapter 4, which we will be using in every stoichiometry problem. So please revise that section and make sure you know how to convert mass to moles and moles to mass. It's a single step conversion. You should know that. Without that, you won't be able to do any problems in this chapter. Did you all follow the steps we did in here? Okay, so this is the figure from your book which summarizes just the concept or steps for mass to mass conversions. Once again, you will be given grams of A represents any substance. Using molar mass of A, convert that to moles of A, and as I said, this is the heart of the problem. Using mole ratio, get the moles of B. Using molar mass of B, convert to grams of B, so that you can go from mass of one substance to mass of the other substance. We will have another example. Well, the same problem, let us just look at this too. What mass of sodium chloride should be produced when 9.20 grams of sodium reacts with 14.2 grams of chlorine? So we are trying to figure out what product, how much product that should be formed. Okay? If you go back to here, we have already done half of the calculations. You can either use chlorine's mass or sodium's mass to calculate sodium chloride. Right? You have to just use the appropriate mole ratio. Let us do with sodium. We have converted the sodium's grams to moles, 0.400 moles. Look at the balanced equation. What is the mole ratio between sodium and sodium chloride? 1 to 1. 2 sodium gives 2 sodium chloride. What does that tell you? Whatever amount of sodium you have in moles, the same number of moles of sodium chloride will be formed. So if you have 0.400 moles of sodium, you should have 0.400 moles of sodium chloride. The question is asking what mass of sodium chloride you will have. So what will you do? What is it we need to do? We already said this one is 0.400 moles. So and this one also will be 0.400 moles. So 0.400 moles of NaCl, multiply that by the molar mass of NaCl, so that we will have the grams of NaCl. What's the molar mass of NaCl? Somewhere around 55. No. How much? 58.44. That's what you said? Okay. Grams in 1 mole. So the mole will go away and you will have the answer in grams. So that will tell you how many grams of sodium chloride is formed. How much sodium chloride? .4 multiplied by 58.44 will give you what? 23 point, I need only one more figure. Did you follow what we did? If not, please ask before we go to the next example. These numbers were already been converted to moles in the previous step, so I'm just using it directly. 9.20 grams is 0.400 moles. We had already done that conversion. That's why I wrote that number just below sodium. Okay? Yes? NaCl smaller mass. Na and Cl from the periodic table. We don't need to use that, as I said. You can either use sodium or chlorine to calculate the product. If you start with chlorine, let's say this also we had converted to moles. This was how many moles? 0.200 moles. So 0.200 moles. That also will tell you this should be 0.4 moles, because see the relationship 1 to 2. So whatever amount of chlorine you have, double the amount of NaCl should be formed. So if you were to use this one, still you have the same number. Okay? So you need only the amount of 1 to calculate the amount of another 1. That's the beauty of stoichiometry. Just 1. That's all you will require. Now here you have a choice which one you want to use. That's what it is. Let us do another activity on mass to mass conversion. Hydrogen burning with oxygen forming water, formation of water, but this is a reaction that uses in shuttle launch, because this reaction, the simple formation of water from its elements, produces lots and lots of heat energy, and that's the energy they use for shuttle launch. And it is a very clean reaction to use, because the product is water which is released as steam to the outside, and that's why you see this big cloud following a shuttle launch. If you see the pictures on TV, or any of you have seen the real one, I haven't, when the shuttle goes up, it releases a lot of hot steam, right? Or you see it's like a hot cloud, and that is all the steam. So this is the reaction they use in shuttle launch. Anyway, if 1.8 into 10 to the power 8 grams of hydrogen is used in a liftoff during a shuttle launch, then what mass of oxygen is consumed? What mass of water vapor is produced? Then the third question is, does the mass of water vapor equals the masses of the reactants? If so, what law is observed? We will do that one, that's just a logical question which is just reminding you of a particular law we learned in chapter 1. But let us do the first two questions. That's what we have been working on. So what mass of oxygen gas is consumed? That is the first question we have to answer. And what we have is the mass of hydrogen. So what will be my first step? Whenever I see mass of something, what do? Convert that to moles. Before even you think about what will be my setup, because you need to do the setup using moles, not using mass. Okay? That is why I keep saying this. Whenever you see mass, grams in a stoichiometry problem, convert that to moles. Then only start thinking about the setup. Otherwise, you might end up using the wrong setup. You will use mass in your setup. So, if I start with 1.8 into 10 to the power 8 grams of H2, I need to convert that to moles. What do I use? 1 mole of H2, oh, not 1 mole, I need 1 mole. Okay. 1 mole of H2 per I'm not using the mole ratio yet. What are we doing here? We are doing the molar mass conversion. So, how many grams? 1.01 is for an H. Are we using just H? So, you need the H2 molar mass. There, everything shows up. That wouldn't help us, right? Oh, come on. Now this eraser is going to give me the trouble. I blame it on Sandra. Okay, what is the molar mass of H2? 2.2 grams of H2. Okay, now we will be at moles of H2. Now, you don't have to do it, each step finishing calculation. We can set it up as one problem, but I'll walk you through each step. So this is your first step. Now you are standing at moles of H2. Now we will use the mole ratio. You need to figure out how many moles of oxygen you require. So now I can use the mole ratio. What is the mole ratio I need to use here? I'm looking for oxygen. So 1 mole of oxygen on the top per 2 moles of H2. That's my mole ratio, and not that again. Moles of H2 and moles of H2 will go away. I'm standing at moles of oxygen right now. Is the question asking how many moles of oxygen you will need? The question is asking what mass of oxygen you will need. So the last step, third step, is converting moles of oxygen to mass of oxygen. Using what? Molar mass of O2. So what is the molar mass of O2? 16 times 2 would be 32 grams of O2 in 1 mole of O2. There, you will have your answer in grams of O2 as the unit. See that all the units also cancel perfectly. So the math we are doing here is, do them at one by one. 1.8 into 10 to the power 8 multiplied by 32 is the only number in the numerator. Then you need to divide that by 2.2 multiplied by 2. I'll leave that up to you which way you want to go. It's all multiplication and division, so as long as you do everything, you should be fine. They both have equal importance. Everyone do it on your calculator rather than just waiting to, look at the answer, so that you will be able to practice how do you enter the number. There is a scientific notation number also. Basically, multiply everything in the numerator, then divide by 2.2 times 2 would be 4.4. What do we get? 1.4 times 10 to the power 9 grams of O2. Is everyone getting the same number? Now, yes, this slide just explains what we did right now. So, as I just set it up, starting with the given mass of hydrogen, first step, converting the grams of hydrogen to moles of hydrogen. Then here is the mole ratio, oxygen per hydrogen. Then converting moles of hydrogen to mass of oxygen. So that's what is explained here also, what you have done. Okay. So when you do the stoichiometry, most of the time, these three steps, we will set it up like this. Again, it's not necessary if it is, clear in your head to do single steps, please do so. You will still end up with the same number. Okay. But your book will be showing this way. That is why I'm showing you how do we set it up, and I'm walking you through the step. When you just look at it, you will be feeling like, oh my God, what am I seeing here? But look at them step by step. At each step what you are doing, things will be clear. And when you look in the example in the book, you will see this. Okay? So first question answered. What mass of oxygen we require? What was the second question? What mass of water is produced? Okay, so that's our second question. Again, we are starting with 1.8 grams of hydrogen. Let me get a screen because I don't have space to. White screen. The first step would be the same, but we will just set it. Uh-oh, not yellow. Yellow won't show up on white, isn't it? Red, so that you can see what I'm writing. Okay, so we are starting with 1.8 grams of H2. First step is the same, converting grams of H2 to moles of H2. So 1 mole of H2 is 2. What did we use? 2.2? 2.02. 2.02 grams of H2. So that step is the same, converting the given mass to moles. So we are starting at moles of hydrogen. Now we are going to use the mole ratio. This time what mole ratio are we using?
2 moles of H2O to 2
moles of water. This time we are looking at water and hydrogen mole ratio. So 2 moles of H2O per 2 moles of H2. So moles of H2 goes away. We need the mass of water. So we need to convert the moles of water to mass using molar mass. That's our last step. What is the molar mass of water? 1 oxygen and 2 hydrogens. 18.02 grams of H2O in 1 mole of H2O. So moles and moles will go away and you will have your answer in grams of H2O. Let's do this math. This is still easier math because this is basically 1, right? 2 by 2 is 1. So 1.8 multiplied by 18.02 divided by 2.02 will give you the answer. Or 1.8 divided by 2.02 then multiplied by 18.02, whichever way you want to do. How many grams of water will be produced? 1.6 times 10 to the power 9 grams of water is produced. Now, there was one more question right here. This is the answer slide explaining what we just did. What mass of water is produced, not that, how we set it up. It's step by step, same process. And the last question was, if you add up the masses of both reactants, does that equal to the mass of the product? Now we have masses of both reactants. We have 1.8 into 10 to the power 8 grams of hydrogen, and what was the mass of oxygen we calculated? 1.4 into 10 to the power 9. Okay, so add up those two numbers. That is 1.8 into 10 to the power 8 plus 1.4 into 10 to the power 9. When you add up those two numbers, is that equal to mass of water? 1.6 into 10 to the power 9. Is that that's what you are checking? Is that true? I mean, you should be getting a number very close to it, at least if not that. You get that, right? Actually, yeah, it's right here. Actually, when you add those two numbers together, this is what probably you will come up with, 1.58 into 10 to the power 9. When you round that off for 2 sig figs, you will have 1.6 into 10 to the power 9, right? And what law describes this? What we just observed? The law of conservation of mass we learned in chapter 1. We learned that in a chemical reaction, you cannot create or destroy any atoms. That means the masses of all the reactants together should be the same as masses of all the products. Since here we had only one product, we just added just the masses of reactants. Let's say in a chemical reaction where you have one more product, like if you add up total masses of both products, that should be the same as total mass of the reactants, because this, even though we can calculate them each one by one, overall every chemical reaction follows law of conservation of mass. Questions so far? I think I have one more example for mass to mass conversion. Here is the question. When aluminum metal is exposed to oxygen gas, a coating of aluminum oxide forms on the surface of aluminum. The balanced equation for the reaction of aluminum metal and oxygen gas is 4 moles of aluminum reacting with 3 moles of oxygen, forming 2 moles of aluminum oxide. Now, here is the question. Suppose a pure sheet of aluminum gas gains 0.0900 grams of mass when exposed to air. Assume that this gain can be attributed to the reaction with oxygen. Questions to answer. What mass of O2 reacted? That is a logical question. When you just read the question, you can answer what mass of oxygen actually reacted. Then from there, what mass of aluminum reacted and what mass of Al2O3 is formed. That's what we have to calculate. So, what mass of O2 reacted in this reaction? What mass of O2? Read this question one more time. Read that sentence one more time. A sheet is gaining this much mass, and that is because of the reaction with oxygen. What does that mean? That means this much oxygen is reacted. It's another, let's get used to the chemical terminology, okay? This is the way the chemists talk. So, this means, all it means, when you read this line, simple language, all it means is 0.0900 grams of oxygen reacted. Okay, so that's the first question. So we have the mass of one of the reactant. From there, we can calculate the mass of the other reactant and mass of the product. So just like the previous problem, we have mass of one of the reactant. So let us start. Let's do number 2 here itself. I'll set it up down here. So we know what mass of O2 reacted, that is 0.0900 grams. So that is the information we have. That's our starting point. So using that, let us calculate what mass of aluminum reacted. So we are starting with 0.0900 grams of O2. What do I do with the grams of O2? Convert to moles. So that is my first step. Conversion please. 1 mole of O2 per 32 grams of O2. Yes, that would give me moles of O2. Now I will use my mole ratio. What is the mole ratio I should use? I am looking for mass of aluminum. 4 moles of aluminum over 3 moles of O2. The mole ratio between aluminum and oxygen, because that's what I'm trying to calculate. So I'm standing at moles of aluminum. The question is asking what mass of aluminum is reacted. One more step. Converting moles of aluminum to mass of aluminum using molar mass of aluminum. Look in the periodic table. What's the molar mass of aluminum? 26.98 grams of aluminum in 1 mole of aluminum. So again, moles of aluminum gone. You have the answer in grams of aluminum. Calculate that please. So it's just that 3 steps. Think of them as each step and write it down so that you won't make a mistake. What mass of aluminum is reacted? .101. So we answer this one, 0.101 grams of aluminum. That's right. Let us see. We need 3 sig figs. Yeah, because we are going to follow rules from here. These 2 zeros won't count. So 1, 2, 3. 3 sig figs is what we need to use. Slide has both set up at the same time. So I don't want to put it up yet. Shall we do the second one? The third question. We will do this one and then we will have a clicker question, and that will be the end of this class. Okay? So what mass of Al2O3 is formed? Let's do that on a different, I'll do a different setup on a different sheet. In color red. Once again, I'm starting with 0.0900 grams of O2. First step is the same, converting grams of O2 to moles of O2. So 1 mole of O2 is 32 grams. Now we will use the mole ratio. You tell me the mole ratio. You guys had the balanced equation. What is the mole ratio between O2 and aluminum oxide? This time we are looking at the product. Nobody wrote down the balanced equation? 4 to 3. 4 was for aluminum. No. 2, we are looking for the product this time, aluminum oxide. So 2 Al2O3 per, what was the number in front of oxygen? 3 moles of oxygen. To be technically right, we need a mole there. So moles of O2 goes away, and I'm standing at moles of aluminum oxide. I want mass of aluminum oxide. So last step, converting the moles of aluminum oxide to mass of aluminum oxide. Calculate the molar mass of aluminum oxide, please. That's what we need to use here. 101.96 grams of Al2O3 per 1 mole of Al2O3. So moles of Al2O3 will go away and you will have grams of Al2O3 as your answer. Do the calculation, please. 0.191 grams of aluminum oxide. Now we can look at the answer slide. Yeah, right there. So, once again, those 3 steps, guys. Starting with the mass of one of the reactant that you know, converting that to moles, using the mole ratio, converting to mass. Okay? Now I have a clicker question. I don't have a full question. When you look at the question, you will see. I'm just asking you to do only a partial step. Okay? Here is the question. This reaction you have seen before, the potassium chlorate decomposition. Here is the balanced equation. The question is asking if 1.24 moles of potassium chlorate, I'm already have given you the moles of potassium chlorate. If 1.24 moles of potassium chlorate is decomposed, how many grams of KCl is formed? So I have done some of the steps for you. I have done that first step. If I were to give you mass of potassium chlorate, I already have converted that to moles. So you need to do only from the second step. Okay, I have given you the moles of the reactant, not the mass of the reactant. So I have done one step for you. Another minute. Not much to do here again, if you know what you are doing. So I'll stop by 4th minute, okay? So please do it before then. What? Yes. Of course I will go over it. Yes. No. No. No, we will not. So this is the first class, so I'm guessing I need at least 2 complete classes and a little bit more. So 2.5 classes. So we will get some time for review, possibly. Oh, 4th minute, and I'm not seeing all the responses, but I'm going to close it, guys. If you want to make a guess, do that now. Otherwise, I'm closing it. $4:30, that's what I'm looking for. There it is. Okay. So 1.24 moles of KClO3. That's what you have. And you are looking for this stuff, KCl. First of all, look at the mole ratio. What is the mole ratio? 2 to 2, or in simple terms, 1 to 1. So whatever number of moles of this stuff you have, same number of moles of potassium chloride will be produced. That principle you used in the lab also. Right? Okay. So 1.24 moles of potassium chloride should be produced. But the question is asking how many grams of potassium chloride is there. So all you need to do is convert the 1.24 moles to grams using molar mass of what? KCl. Oh, there is my pen. So the setup would be 1.24 moles of KCl multiplied by, what is the molar mass of KCl? 74.55 grams of KCl in 1 mole of KCl. So moles and moles will go away and you should have your answer. What should be our answer here? Wow. $92.4 would be your answer. Okay, we will stop right here. Please revise the mole mass conversion and this topic before next class, because we are adding on to this in next class. Okay? If you don't get this, next class is complete waste. So make sure you get this.
Me and Liz are wondering what time you were in your office again.
Say that again?
You said you have you go to
I-
your office. What day is it? Monday and Wednesday, right?
Monday is 10 to 12, not Wednesday. Wednesday I'm teaching a lab at that time.
Okay.
Okay?
So we can come in.
You, not in the office though, I will be in J400.